Hi guys, so go ahead and pull out your notes from last time. That would be the glass analysis notes. And then make sure that you have a highlighter and we will get started in like a minute. This is the slide that I think you're currently on. I really hope this is the slide you're currently on, because to be honest, I don't really remember exactly which slide we left off on, but I'd say about 75% sure that this is it. So it's probably about, I would say, a third of the way through your packet. All right, so let's jump in. Just as normal, the things that I want you to highlight and to pay attention to, that's the stuff that I'm going to be underlining, probably in red in this situation. So on this slide, we're talking about how we're going to use glass in a forensic investigation, or how we can use it as evidence when we're running through our forensic analysis. And it's going to comprise of 3 steps. First and foremost, you're going to have to be able to find the glass, then you have to measure it, and then you have to start comparing your glass from your crime scene or your suspect to some known samples, some things that you know for a fact. I know this piece is Pyrex, I know this piece is regular glass, or whatever the case may be. So that's what we're about to delve into. Okay, just a quick reminder before we start talking about the measurements, that we have 2 kinds of characteristics that will eventually lead to 2 different types of evidence. So things can have individual characteristics just as well as they can have class characteristics. So remember that your individual characteristics are going to be unique or special to a single person or a specific item. It's going to be something that just that person has, or only that object has. Nothing else has it. Okay? Whereas your class characteristics are going to be common or shared in a group. Okay? A bunch of people have brown hair. A bunch of people have size 7 shoes. So keep in mind both of these things, and we're going to try and figure out where exactly glass falls between individual versus class characteristics. Now, glass can have individual characteristics, but getting it to that point is a little bit tedious. So we very rarely do this, but I just want you to be aware that this is a potential thing. So individual characteristics happens when I can take all of my glass fragments and I can piece them together almost like a puzzle. So again, only occurs when my fragments can be fitted together physically. For you to do this, it means that you have to have every piece of glass, every section, every shard of glass, and then you have to sit there and puzzle it together just like you would if you were building a puzzle. So you want to make sure that all the edges line up and they match, and that you're using the patterns that the glass pieces broke into to help you to figure out what piece goes where. Most glass evidence is going to either be too small or in too many pieces for a scientist to sit there and do this. So we very rarely use this method. So let's go ahead and write that in. It's rarely used. All right. Next slide. So if we're not going to sit there and piece all the pieces of glass together, then what are we going to do? Well, we're going to use and we're going to rely on class characteristics, and we look at 2 of them in particular. We look at the characteristics of density and of refractive index. So the way this works is all types of glass will have a specific density. So soda lime glass will have one kind of density, and crystal will have another kind of density. They'll also all have refractive indices, which I'll explain what that means in a little bit. So what I'm going to do is I'm going to take my piece of glass that I found at the scene of my crime. I'm going to use its density. I'm going to calculate its density, and I'm going to calculate its refractive index, and then I'm going to compare those numbers to samples that I already know. Okay, so I know that this piece has a density of this. My piece had a density of this other number. These 2 don't match up. That's kind of the basis on which we think about this. All right, so like I said before, we can use density to match up glass fragments. So for example, I could know that my piece of glass, let's call it piece A, has a density of 3.7 grams per milliliter. Okay? And I can, let's say this is my known sample. Oops, sorry. Okay, so this is my known, oh my goodness, known sample. Y'all. Now, piece B, let's say I got this from my suspect. It might have a density of 2.7 grams per milliliter. Because these two numbers don't match up, this tells me that glass B and glass A could not have come from the same source, so they're not the same type of glass. So this is called comparing your evidence piece, which would be piece B in this situation, to a known sample, which is piece A in this situation. Okay, so density is calculated by taking the mass of an object or substance and dividing it by the volume of said substance. And this is the resulting formula. Density is mass over volume. There can be two, you're going to have to write this in, there are two different sets of units that we can use with density. So if the object is solid, then the density can be in grams per centimeter cubed. But if the object is liquid, or we used a liquid to find the volume, then it'll be in grams per milliliter. Okay, so those are your two units for density. All right, so go ahead and make sure that you've added that to your notes. Okay, this next slide just gives you an example of how to work through a density problem. Remember, there are a couple of ways of finding volume, so let's talk about that really quickly. Okay, so if it's a dimensional object, a solid dimensional object, I can use the formula length times width times height. But if it's not a solid object, so let's say it's a weird shape, like a sphere or a circle, like think of marble, for example, then I can use the displacement method. And remember, in displacement, I'm going to take a known amount of liquid, so let's say this is 20 milliliters. Okay, I'm going to drop my object in it, which is going to make the water level rise to, let's say, 30. Okay, so then now all I need to do is take the 20 away from the 30, which means that my object has a density of 10 milliliters. So that's one more method. And you're familiar with both of these. This one, this first method, you learned in math. This second method you've seen in science before, and we did it in our measurement lab back in the first 6 weeks. So with this example, you can just kind of read through it, but it should make perfect sense to you. I'm going to teach you one more method, which will be on the next two slides that's coming. So next slide coming up. Another method we have for figuring out density is by using what's called the flotation comparison. And we use the flotation comparison when our pieces of glass or our objects that we're trying to find the density of are so small that it's hard for us to get a good measurement on mass or a good measurement on volume. So you take your sample and you drop it into a specific amount of liquid. And I didn't say water because we can use any liquid for this, as long as we know what the density of that liquid is. If the object is denser than your liquid, then it's going to sink to the bottom of the liquid. Whoops, sorry. Like it shows you here. Okay. So if it's denser, it sinks. You should be filling this in on your slide along with me. Now, if the sample is less dense than the liquid, then the sample will float on top of the liquid, which is what this image shows here. Now, if the sample has the same density as the liquid that it's in, it will achieve what's called neutral buoyancy. And that means it neither sinks nor it floats. So let's say that the density is the same for the liquid and the solid. Okay, so based up here, we're going to say, excuse me, that if the liquid is denser, then we're going to, actually, no, hold on, sorry, let me erase this. Okay, so here I want you to know what neutral buoyancy is. It only happens when the object neither sinks nor floats, and it means that it has the same density as the liquid that it's in. Okay, we can go ahead and skip over this slide. This slide just talks about how we would keep on using the same procedure if we had multiple samples. So just go ahead and turn to the next slide. So the next form of measurement is called refractivity. Sometimes it's referred to as refractive index. I need you to know that this is a number. It's going to be a value, just like how density was a value. And let's really quick just go over what refraction is. The last time you would have seen this would have been in your physics class or principles of technology. So refraction is a measurement of how much an object slows light down. And one of the ways that we know it slows light is it causes the light to bend. Okay, another way to think of this is that it causes light to change, it causes light to change direction. Okay, so think of if you've ever dropped like sunglasses or anything really in a swimming pool and you reach over to pick it up. You reach in one direction, like you really think that this object is on one side, when in truth and in fact it shifted down a little bit. And that's because as light moves from air into water, it slows down and it bends. And because it bends, your eye interprets that as if the image has moved across, when in truth and in fact the image is still in front of you. Another way we see this sometimes is if you, let's say you're drinking out of a transparent glass and you're drinking water and you have a straw in that water. Sometimes depending on how you're looking at it, it looks like the straw is broken and it's off to one side. All of that is because of refraction. So we can actually measure it. We can measure how much the light ray slows down as it moves from one object to the next. So just like how different kinds of glass have different densities, different types of glass also have different refractive indexes. So we can use that number to help us to figure out what kind of glass our piece from our suspect or our piece from our crime scene could potentially be, or what type of glass it could potentially be. So how we use this property of transparent material, is kind of similar to how we would do the flotation device in with glass for density. It's all about taking the glass and putting it in a liquid. So we're going to choose a liquid that we know the refractive index of, and we're going to then take our piece of glass and dip it into that liquid. What we're looking for is either can I see the outline of this piece of glass in this liquid, or can I not see the outline? And each of those things will tell us a different piece of material. So if I take a piece of glass and I put it in a liquid, so I was saying if I take a piece of glass and I put it in a liquid that has a different refractive index to that piece of glass, I can see an outline of that glass in that liquid. So this might be hard to see on the video, but I'm going to try and draw it in black. So starting off with this picture right here, if you look for my laser pointer, it's the one that I'm circling. Okay, there is a black outline right here and another black outline right here. That would be the outline of a piece of glass. That outline is known as the Beck line, and that tells me that this piece of glass does not have the same refractive index as the liquid that it's in. Because I can see that Beck line, or because I can see that outline, I know that the liquid and the glass have different refractive indexes. Okay, now I'm going to choose a different color for the next one. Right here, there's an outline of a piece of glass. It's very, very faint, almost to the point where you can't see it. Okay, because I can't clearly see it, it tells me that this piece of glass and this liquid have the same refractive index, because that glass disappears in that liquid. So we're going to say that the liquid and the glass have the same refractive index. And it's because you can't see it. Whoops, that was a bad E. That's as good as I can get it. Okay, so hopefully that kind of made sense. If you need to ask me questions, just feel free to star like this slide, and then we can talk about it when I get back to class next, well, after Thanksgiving. All right, so to go over the information one more time, remember that as light moves from one medium to the next, it slows down or it bends. So if the glass bends the light at the same angle as the liquid, then my Beck line is going to disappear and my glass seems to disappear, and this tells me that they have the same refractive index. So I need you to underline. Pretty much all of this is important, really. So when light passes through a piece of glass in a liquid with the same refractive index, keyword here being same refractive index, this is what's going to happen. The glass is going to bend the light at the same angle as the liquid. The Beck line will disappear and the glass appears to disappear. Okay? All right, so now let's talk about glass fracture patterns. So every object has a certain amount of elasticity or stretch. So let's write in the word stretch. Okay? Something will only break when you push it beyond its elastic limit. So glass breaks when its elastic limit is exceeded. When that happens, it produces fractures when it's penetrated by something, a bullet or a ball or a bat or a brick or whatever you can think of. And some of these patterns become really important to forensic work. So we're about to talk about what those patterns are, what they look like, and how you can tell which of the patterns you're seeing. Okay, so the first kind of pattern I want to talk about are called radial patterns. And I need you to know that they are the patterns that are made first. They're the very first pattern to form when a piece of glass breaks. They form on the side opposite of where the impact hit. So they always form on the opposite side of the impact. So think of it this way. Here is my piece of glass. Okay, think of it as a thick pane of glass, if you will. All right, that's as good as I can get before the drawing starts getting crappy. So let's say that I have a bullet moving this way, okay? And it's going to hit on this side of the glass. That radial pattern is going to form on the back end. So the radial pattern forms over here. Okay, so the radial will form on that side, but the bullet, oops, let's make that better. Sorry about that, guys. The bullet will hit on this side. Okay, so the radial pattern forms on the opposite side from where the bullet hits. The next thing I need you to remember is that with radial patterns, they always terminate, and in this case, terminate is a fancy way of saying end. So they always terminate or end in an existing fracture. I'll make this make more sense in a couple of slides. But this is super important to things like helping us to figure out who shot first, or if there are multiple shots, which shot was the first, which one was the second, which one was the third, etc., etc. Okay, so on this diagram, these will be your radial fractures. They're kind of diagonal. They start in the middle and they move outward from the, whoops, well, you know, not like that, but they move outward from the middle of the gunshot. Whoops, oh boy, now I'm just making a mess. Okay, so all the ones that I outlined in red, those are your radial fractures. The next kind of fracture is called a concentric fracture, and concentric fractures form second, so they form after radial fractures. Okay, so I need you to know they form second. I also need you to know that they encircle the bullet hole. So if here's my bullet hole, my concentric fractures are going to form around it. Kind of like that. I always think of a bullseye or a target when I think of concentric fractures. I need you to know that they start on the same side as the force or the impact. So again, here's my piece of glass. Okay, and my bullet is coming this way and it's going to hit there. My concentric fractures are going to form on the same side as the bullet. So they will form here and here and here. Form on the same side, okay, not on the opposite side like radial. And on this diagram, these are the concentric fractures here. They just kind of go around in a circle for the most part. So I said that we're going to have to use those radial fractures again, and this is kind of where they would be used. We use them when we try to determine the sequence of multiple bullet holes or multiple gunshots. So remember we said that radial fractures will end or terminate into fractures that were already there. So we're going to use that to help us to figure out which bullet hole came first and which shot came first. I will do more explaining on the picture that follows this. We can also use our radial fractures to determine our first shooter, but then we can also use the size of the entrance and exit holes to determine first shooter. So I need you to know that we'll use radial fractures to determine the sequence of shots or bullet holes, and we can use them again to determine the first shooter, but we can also use the size of your exit and entrance holes to determine the first shooter. Okay, so it's not the best picture. It's a little fuzzy, but we're going to make it work. So the first thing I'm going to do is in blue, I'm going to go through and I'm going to highlight anywhere that two lines meet or touch. So that would be here, here, right here, and here, and up here. Okay, so 1, 2, 3, 4, 5 different spots. So remember that I told you that radial fractures will end if another fracture was there first. It'll move and move and move, and then once it touches another fracture, it'll stop moving. So I'm actually going to erase this. And I don't know if I'm going to try zooming in. I don't know if this is going to work or not. It might be a little fuzzier, and it doesn't work. Well, I tried. Okay, so, sorry, that didn't, oh wait, hold on. I think I might have a zoom button. Or not. Just kidding. Yeah, never mind. That didn't work, guys. Anyway, so let's go back to this first one. I'm just going to draw a bigger box around it so you know where I'm focusing in. And then I'm going to change some colors a little bit. Sorry. Okay, so this line right here is one fracture. And this line right here is another fracture. Notice the line that I just colored red does not pass the black line. It stops right at the black line. The only reason it would do that is if the black line was there before the red line. So the way we work these out is we find where they meet, we figure out which one stopped moving, which one doesn't go beyond the next. So like, see, there is no red line. See how there's no red line over here? That tells you that the red line stopped right at this point, which means that this black line, well, I colored it in black, was there before the red line formed. So once I can figure out which line was there first, I will then trace backwards to where that original entrance point was, and that tells me that this particular shot came before this shot. So that's how I know that this one is number 1. If I need more proof, I can go down to these two areas here. And if you look closely, you will see, let's color this one red. So here's my red line again. Whoops, sorry, wrong button. Here's my red line again, and here's my black line again. And notice, again, my red line stops when it meets my black line. If I trace back to my red, this is the original entrance point. If I trace back my black, this is the original entrance point. Again, this tells me that this bullet hole, or this shot, was fired before this shot. So this becomes shot 1, and this becomes shot 2. Now, just to make sure that this shot down here really was fired last, I of course can look here. I can see that, let's make this shot blue, I guess. It stops right here. whereas my black stops right here. So it still tells me that this shot on top came before this shot on the bottom, but it doesn't tell me if this shot is number 2 or number 3 just by looking at this one point. So now I'm going to come over here. Notice how here's my blue shot and it stops. Here's my red shot. Okay, the fact that this blue shot stops right here into this red shot tells me that this red shot existed before this one, so this is shot number 2. So it's not so hard once you're actually doing it with paper and pen, you know, or pencil in front of you, as long as you remember that the only way that fracture is going to stop is if there was a fracture there already. So if it stops, the fracture on top of it or underneath it was there before. Okay, we will do more practice with this when we come back from Thanksgiving breaks. If you don't completely understand right this second, that's okay. There is still more time to practice it. Okay, the other thing that we can do with fracture patterns is we can determine the direction from which the bullet was fired, and that's actually a really useful thing. So we can figure out if the person fired from outside of the home into the home, or if the person stood inside of the house and fired out into the street. And the way we do that is we compare the size of the entrance hole to the size of the exit hole. So let's talk about exit holes. Exit holes are always larger. It does not matter what kind of material we're shooting through or anything like that. The exit hole is always larger. When we're talking about glass, normally the larger piece of glass is pushed out or knocked out of the surface where the bullet is leaving. And again, that's because glass is elastic, so it's going to bend or bow in the direction that the bullet's traveling when it's hit or when it's struck. Okay, still talking about entrance and exit holes. This time we're focusing in on the entrance holes. So the bullet always makes a very small and neat hole wherever it enters. And again, it doesn't matter what the material is. The glass is normally going to be blown back in the direction that the bullet is traveling because it's elastic. So the glass always blows back in the direction of impact because it's elastic. So think of the big window at the back of my room. If someone stayed in the parking lot and shot through that window, there will be more glass inside of my room than there will be on the sidewalk outside of the window, because the bullet is traveling into the room and the glass gets pushed in the direction that the bullet is traveling. All right, so here's a little visual to help you with this. I'm going to color some lines in to make it a little bit more obvious. So this point right here, that's where my bullet is going to hit. And hopefully you can see these black lines that radiate this way. These are the lines that I'm coloring in. Feel free to color those in on your image just to make them a little bit more sharp and clear. These lines represent the force that's going to push through and travel through with this bullet. This is the area that's going to get the majority of the force coming from the bullet. Okay, so when that bullet does push through, so look at the other picture, notice the big crater it creates on either side. Okay, all of this was once glass material that got moved or pushed away because of the force of the bullet. So here's my entrance, nice, small, neat. And then this is my exit, way bigger. So that's one of the ways that we can tell the direction. Wherever the entrance is always going to be a smaller section, whereas the exit's always going to be a bigger crater type section. Okay, so another kind of mark or fracture are called, we generally call them stress marks. Sometimes we refer to them as conchoidal lines. That's the technical name, but most of us just call them stress marks. So these are marks that are found on the side of a piece of broken glass. And these lines spread away from the point of impact. They move away from where the bullet hit the actual glass. The lines have two specific patterns. They are parallel on one side of the piece of glass, and then they turn and become perpendicular on the opposite side of the glass. So again, let's do some highlighting. So again, these are marks found on the side of broken glass. They spread away from the point of impact. They are parallel on one side, and then they turn and become perpendicular on the other. And they're made by both radial and concentric fractures. So you're not looking at the piece of glass flat, you're turning it on its side and looking at it. And one of the things that we use is this thing called the 4R rule, which stands for on radial cracks, ridges make right angles to the rear. And I'll show you an image of what that means in a second. Okay, sorry about that, guys. The drawings that you have, I had to draw into your PowerPoint myself, and those didn't translate over into the video, so I had to redraw at least one of them really quickly. But I just wanted you to understand the difference between the parallel side and the perpendicular side. So the parallel side has these lines that run pretty much all the way straight down until all of a sudden they turn. And when they turn up at these right angles, like here and here, that's going to be your perpendicular side. You will look at some of these in your observation lab today, and then we'll do a little bit more work with them when we come back from Thanksgiving. So now we're going to talk through how we collect glass as evidence. A lot of this is stuff that you already know, so I'm going to go ahead and just kind of highlight the ones that are key to glass only for the most part, or just specific or special circumstances you might see with glass. So just like with everything else, we're going to identify and photograph all glass samples before we move them, but we especially want to try and identify what part of your glass was considered the outside surface versus the inside surface. The other thing that we try to do is collect large fragments, so it makes it easier for us to get some of those measurements of density and refractive index. It's easier to get those from a bigger piece of glass than it is from a little tiny shard of glass. The other thing that would be important, and I mean, you kind of would do this regardless, but you want to indicate the relative position of multiple window panes in a diagram if that was something that you saw at that particular crime scene. If all of this could have come from one window, you want to be able to denote that in your sketch. If all of the glass could have come from multiple windows, you want to show that in your sketch as well. One of the reasons that glass is such useful forensic evidence is that it's amazing at picking up extra trace evidence that your perpetrator may never have even thought of leaving behind. So things like if I broke a window to try and open a door, or I broke a window to climb into a building or into a home, there's a really good chance that I might have left behind little bits and pieces of myself that I didn't plan on doing. Remember Edmund Locard's principle of exchange. So if I rub up against it, I might leave some skin cells if that glass scratched me. I might leave blood behind. I might leave hair if it gets caught. I might leave fibers from my sweater or my shirt or my pants or wherever. So all of those things become important to look for. You'll always find that your analysis is going to include looking to see if there's anything other than glass on the glass. And of course, there are things like fingerprints. We can even talk about leaving traces of drugs on glass, just depending on the nature of the crime and the location of the glass. Just like we would do with every form of evidence, you're going to go ahead and package it as properly as you possibly can, making sure that you maintain your chain of custody. And then we also separate glass by its physical properties. So we look at things like size and color and texture. You wouldn't put smooth glass and textured glass and stained glass all together in the same bindle or in the same container. You would separate those out. Now, if you were to find other forms of trace evidence on your glass fragments, you would want to go ahead and separate those out from the glass as well. So you would take swabs of blood, you would take the hair out and put it in its own separate container, you would take fibers out and put them in their own separate container, that kind of thing. Another thing that we do is you would examine any clothing, so clothing from the suspect, clothing from the victim, that could have possibly been on or in or at, let's say, that crime scene, because especially when the shards break into really tiny pieces, it's really easy for those pieces to fall into the nooks or folds of someone's clothes, and the person may not realize that they're there. So it's a good way to tie your suspect to your crime scene. All right, so at this point, I need you to listen really carefully to the instructions I'm about to give you. You are going to divide into kind of half the class and half the class, but I'm going to control who goes where. So you, again, still need to listen. Half of you, approximately, are going to start working on that lab station rotation. There are samples set up on station 1 through station 4. Read what's on your sheet of paper. This is the glass observation lab that you picked up when you walked in, and that will tell you what you need to do at each station. If I don't call your name, you're not starting with lab. You are going to do a different activity. So just sit patiently, get out your phones, sit patiently, and wait for my further instructions. Again, those are the people who are not doing lab. So listen up for your name. If I call your name, you are moving to a lab station. You are going to work in groups of 4, okay? So 4 people to a station. All right, let's see. Cynthia, Roberto, Hector, Lupe, Grace, Chloe, Abel, Sarah, Jocelyn, Leslie, Jordan, Vanessa, Christy, and Diego. You guys are starting with lab. So you're going to take a pencil and you are going to take that glass observations lab sheet and you are going to move to the lab stations. Again, you are working on stations 1 through 4. Okay, so go ahead and move. Okay, and you guys are just going to coordinate your own cells. You're just going to move from station to station. You'll have about 20 minutes, give or take. That should take, actually, let's say 15-ish minutes. That should take care of you doing lab. Okay, everyone else whose name I did not call, go ahead and grab a calculator from the blue bucket at the front of the room and then take your seats.